Howdy, and welcome to Mean 315 Principles of Thermodynamics, lecture number 14. Okay, so to begin, we have a few announcements. First of all, homework number 6 is due on Tuesday, October 15th by 3 o'clock outside my office door, which is 321 Mechanical Engineering Office Building in the wire basket that's outside my office there. And of course, the homework is due at that location because there is no lecture on Tuesday, October 15th. So much like today's lecture number 14, which is an online lecture, Tuesday's lecture number 15 will also be an online lecture. And I'll have that video ready and available to you by class time on October 15th. If you've not already filled out the mid-semester course evaluation, actually, you can go ahead and hit the pause button since you would have had to have gone into e-learning to get this video and go fill out the course evaluation right now. It should only take you maybe 5 minutes at most, but you need to do it by Sunday, October 13th at 6 o'clock p.m. We're asked to make the evaluation available for 1 week, and so that October 13th date at 6 o'clock p.m. is the 1 week mark. So please be sure to fill out the mid-semester course evaluation. Your feedback is very important to us. And then finally, last announcement, project update number 2 is due on Thursday, October 17th in class, which is the next time that we are all getting together as a class. Okay, so where did we pick up last time in our discussions? If you remember, when we finished class on Tuesday, we were talking about the ideal work process. And we talked about the ideal work process in the context of a turbine, but it really applies to any steady state or what I'll call an open system workflow or work transfer process. So the basic idea, if we write it in the context of a turbine, is if we have an inlet state and we have a certain exit state, part of the exit state is defined, and I'll get to that in just a moment, what's the maximum amount of work that this turbine can make? So we already determined this. We determined this in class on Tuesday, and we said that if we had a given inlet condition and if we make the turbine adiabatic, then the way that we can get the maximum work from the turbine is to allow the exit state to go to the lowest energy state as possible. So how do we know that that'll give us the maximum work? Well, let's take a look at the first law. The first law, of course, as we write it for a steady state system, says that Q plus HI is equal to W, the work transfer, plus the exit enthalpy. So we already established that to get the maximum work from our device, it needs to be adiabatic. So the Q term goes to 0. And the first law then tells us that the work is equal to HI, the inlet enthalpy, minus HE, the exit enthalpy. And what we said on Tuesday was that if we want to maximize W, then we need to maximize the difference between HI and HE. Since HI is fixed, that's a given condition to us, then the way that we maximize that difference is by making the exit enthalpy as low as possible. So to maximize the work from our work device, then we need to maximize HI minus HE, which means that we may need to make the exit enthalpy as low as possible. So then the question becomes, what is as low as possible? In other words, what can HE possibly go down to? And so the way that we answer that question is by using the second law. Remember that the second law tells us if a process is possible or not. And what we're saying is that we want to get the maximum work from our work device by making HE as low as possible. Well, the second law is going to tell us how low the exit state can be that is theoretically possible. So if we look at the second law, and we recognize that we're modeling this process as being ideal, so that means that the entropy generation is equal to 0. So when we write the second law, we get that the exit entropy, SE, is equal to SI plus Q over T plus the entropy generation, Sgen. We've already established that the turbine is adiabatic, so our Q term here goes to 0, making the Q over T term equal to 0. And we established that the ideal turbine, that the turbine that'll make the maximum amount of work, means that it must be a reversible turbine, so the entropy generation is equal to 0. Remember that when entropy generation is equal to 0, that's the case of reversible process, or what we call the ideal process. So our second law tells us that if we're going to call this an ideal device, an ideal process, where ideal means that it's adiabatic and entropy generation is equal to 0, then the exit entropy is exactly equal to the inlet entropy. In other words, we've not added any disorder or any chaos, if you will, to the energy that flows through the system. So for this ideal work process, the exit entropy is equal to the inlet entropy. And when we have this situation where the exit entropy is equal to the inlet entropy, or where the entropy stays the same through the process, we call that an isentropic process. And we learned about that earlier this semester. We had a homework actually that had us explore isentropic processes. And now you know that the isentropic process, in fact, is one which is an ideal process. Okay, so what that means, though, getting back to the original question, is that the lowest possible exit state from this ideal turbine is one when the exit entropy is equal to the inlet entropy. Okay, so hang on to that thought, because now the question that we can ask is, how does this necessarily translate to maximum work in an application or a device? In other words, if I know that I have this defined ideal process, which is adiabatic and reversible, what does that mean for an actual application? Or how does that confirm for me that I'm going to get maximum work from my device? Well, let's continue to consider our turbine, and let's now suppose that it's a real turbine. Okay, so we're real engineers, and we have to deal with real equipment, real technology. So real things like entropy generation are going to be present in our real devices. So we're going to consider a real turbine such that the entropy generation through that turbine process is greater than 0, right? That's the only possibility. If the turbine's not ideal, the only other possibility is that entropy generation is greater than 0. So even though it's a real turbine, we are going to impose the assumption that it's an adiabatic turbine, and we can realistically do that, by using lots of insulation, for example, that we might shroud around the turbine, so that we trap that thermal energy, prevent it from flowing into the surroundings. So it is actually reasonable to make an assumption that the turbine is adiabatic. So we have a situation where we have a real turbine. We are assuming it's adiabatic, but because it's a real turbine, it has irreversibilities, so entropy generation is greater than 0. Okay, so how do we analyze this? Well, here's our diagram of our real turbine, and we have an inlet state, and we have our real turbine, and this real turbine is now, I'm going to subscript this, is now producing some real amount of work. And because it's transferring some real amount of work out of the turbine system, the exit state is going to be associated with that real process. And so we call the exit state E, real, meaning that this is the exit state that corresponds to the real process, the real turbine process. Okay, so let's do a first law analysis, and I'm just going to cut right to the chase since we know how to go from the general steady state equation to the specific situation that we're analyzing. So we have this real turbine, and we know that the real work is equal to the inlet enthalpy, HI, minus the real exit enthalpy, HE, real. So that's how we would calculate the real work. And we would have to have some information that would fix for us the inlet enthalpy and some information that would fix for us the real exit enthalpy. But doing a second law analysis, will reveal some insight for us to know how this real work compares to the ideal work. So the second law tells us that the exit entropy for the real exit state, so SE comma real, is equal to the inlet entropy plus entropy generation. Remember that this is a real turbine, so this S-gen term is going to be present and it's going to be positive. Okay, so now we've already established that the inlet state is fixed. This inlet state is going to be the same regardless of what device is downstream of that inlet state. In other words, this inlet state is not influenced by what happens downstream of it. And so our inlet state I doesn't require any subscripts. But as I mentioned on the exit state, because the exit state is what results from the substance having gone through the real process, it's going to have a state that corresponds to the real exit state. But there is one thing that is fixed on the exit state. And in the case of, say, turbines, and later on, as we'll talk, compressors, that one property that is fixed at the exit state is the system pressure. The reason why is that pressure is in fact controlled by something downstream of the turbine. So what does that mean? Well, let's suppose that this turbine was exhausting to the atmosphere. Okay, let's just suppose that there was nothing attached to this exit pipe and that whatever was flowing into the turbine was just flowing out into the atmosphere. Well, that atmosphere applies back pressure on the turbine. So the exit state can't go to a pressure lower than the exit pressure, lower than the atmospheric pressure, because the atmosphere is applying a back pressure on the turbine. And so that's one example. Let's suppose instead that there was, for example, a condenser that was downstream of the turbine, and then let's suppose that there was a pump over on the other side of the condenser. Well, that pump is pulling a vacuum through the system as it draws the substance into the pump and pressurizes it back into the boiler. By virtue of that pump drawing a vacuum on the condenser located here, and then eventually on the turbine's exit state, that pressure is a boundary condition to the turbine. So this exit state's pressure is actually controlled by the vacuum that's being pulled, or the negative gauge pressure, if you will, that's being pulled by this pump. So the point is that this exit state pressure of this turbine is controlled by something outside of the system. It's what we call a boundary condition. And pressure is a boundary condition to a steady state work device, whether it be a turbine, a compressor, or a pump. Okay, so what that means is that we have a fixed inlet state and we have a fixed exit pressure. So in the case of the inlet state, we may, for example, know what the inlet temperature is, the inlet pressure, inlet enthalpy, inlet entropy. That's prescribed. That's going to be true regardless of what happens downstream of that inlet state. So we say that the inlet state is fixed. And it's, you could even say that that's a fixed boundary condition. Likewise, the exit state pressure, PE, is a fixed boundary condition. Okay, so in other words, regardless of what happens through this turbine process, the exit pressure is always the same. It's a fixed boundary condition. Okay, so with that information, knowing that our inlet state is fixed, and knowing that our exit pressure is fixed, and knowing that this equation gives us our real work, and this equation tells us how the entropy behaves through the process, we can look at all of this on TS and pH diagrams. And by doing that, it helps us understand what this maximum work means if we were to evaluate an ideal device. We'll get to that in just a moment. We're still just focusing on the real device. Okay, so here are our beloved TS and pH diagrams. So of course you had these on exam number 1. don't worry, you're going to have these on exam number 2 and the final exam as well. So it's certainly well within your best interest to become familiar with generating these diagrams. So on our TS diagram, we of course have temperature on the y-axis and entropy on the x-axis. And we have our pressure, line of constant pressure that corresponds to the inlet state. And of course, a turbine is expanding the substance, which means that the inlet pressure is going to be higher than the exit pressure. So this line of constant pressure here is that which corresponds to the exit state pressure. We then have our inlet temperature, Ti, and so our inlet state is fixed by where the inlet temperature line crosses the inlet pressure line. So this black circle here indicates our inlet state. Okay, now let's suppose, for the sake of discussion, that I didn't have this TE real drawn here or this E real drawn here. Okay, it's a little bit hard to show with the video lecture, but if I were doing this in class on the board, all I would have drawn at this point is the line of constant pressure inlet, the line of constant pressure exit, the line of constant temperature inlet, and I would have said this black circle is our inlet state. Okay, all the other features on this diagram wouldn't have existed yet. Okay, so where is that exit state? Well, we know that the exit state is somewhere along this line of constant pressure, the exit pressure line. And remember, that exit pressure is fixed regardless of what the process is, whether it be a real process or an ideal process. So from the second law, we know that the exit entropy for the real turbine is going to be greater than the inlet entropy. How do we know that? Well, our second law equation tells us that SE real is equal to the inlet entropy plus the entropy generation. And since entropy generation is greater than 0, that tells us that exit entropy for the real device is greater than the inlet entropy. Okay, well, let's go back to our TS diagram. What that means then is that the real exit entropy is somewhere to the right of this inlet line, this inlet state. In other words, if I were to draw straight down to here, this is the case where the inlet, this is what the inlet entropy is equal to. But the real exit entropy is to the right of this line because the real exit entropy is greater than the inlet entropy. So I just arbitrarily chose this point here as being my real exit state because it's along the line of constant pressure that corresponds to the exit state pressure, and it's at an entropy that is greater than the inlet entropy. So now that I know that this is my real exit state, I then draw this line over here and say that this is my real exit temperature. Okay? Now hang on to that thought for a minute. What we glean from this information, first of all, is that the exit real temperature is less than the inlet temperature. Now let's take those two pieces of information, right? The fact that well, I guess it's just one piece of information, I'm sorry. Let's take that one piece of information, that the real exit state temperature is less than the inlet temperature, and let's go over to our pH diagram. So over here on our pH diagram, now what I can draw is, of course, pressure on the y-axis and enthalpy on the x-axis. And I can draw my two lines of constant temperature. So this line up here is my Ti. It got cut off over here, but that's my line of constant temperature corresponding to the inlet temperature. And because I know from my TS diagram that the real exit temperature is less than the inlet temperature, I can draw my line of constant temperature for the real exit state lower than the line of constant temperature for the inlet state. And then I can just say, well, I'll arbitrarily say that this is my inlet pressure, and so this is my inlet state, and then I'll arbitrarily say that this is my exit pressure, so that this is my real exit state. And so now this, if I drop down here to the h-axis, this point here corresponds to my inlet enthalpy, and if I drop down here, this point corresponds to my real exit enthalpy. And so my work transfer is the difference between those two numbers, HI minus HE comma real. That's my real work transfer. Okay, so now let's use this information and let's follow this same process to analyze the ideal turbine. Okay, so in the case of the ideal turbine, now what we do is we say that this is our ideal turbine and it has the same inlet state as the real turbine. It produces a real amount, an ideal amount of work, and because it's producing an ideal amount of work, the exit state corresponds to the ideal exit state, or E comma ideal. So from the first law, we get that the ideal work transfer is equal to the inlet enthalpy minus the ideal exit state enthalpy. And, as we already showed above, the second law tells us that the ideal exit entropy, SE comma ideal, is exactly equal to the inlet entropy because our entropy generation is equal to 0. Okay, now, so let's draw the ideal process on our TS and pH diagrams. So here's our TS diagram. Let's first focus on the TS diagram. And we have still the real exit state on here. So we have our inlet state pressure and our inlet state temperature. So we have our inlet state I here. And we have our exit pressure and our real exit entropy. So we have our real exit state drawn here. And we have our ideal exit entropy, which is equal to the inlet entropy. So this is our ideal exit state, which of course is on the same line of constant pressure as the real exit state because this pressure is a fixed boundary condition. That exit pressure is a fixed boundary condition regardless if it's a real or ideal device. So this is where our ideal exit state is located, and that tells us what our ideal exit state temperature is. And the important information that we've just gotten from this TS diagram by doing all this analysis is that the ideal exit state temperature is less than the real exit state temperature. So let's use that information, the information that the ideal exit state temperature is less than the real exit state temperature, and let's look at our pH diagram. So we still have our inlet conditions. So this is our line of constant temperature at the inlet. Again, I apologize that got cut off there. And we have our line of constant pressure at the inlet state. So this is our inlet state I. And then as before, we have our line of constant temperature corresponding to the real exit state. And based on our analysis of the TS diagram, we know that the ideal exit temperature is less than the real exit temperature. So this is our line of constant temperature corresponding to the ideal exit state. We then have our exit pressure. And so where the exit pressure corresponds to the real exit temperature, that is our real exit state, E comma real. And that gives us our real exit enthalpy. Likewise, again, because that exit pressure is a fixed boundary condition, it's the same for real and ideal devices, where we have the exit pressure, the line of constant pressure for the exit pressure, intersect the line of constant temperature for the ideal exit temperature, that gives us our ideal exit state. And if I drop that down to the h-axis, that corresponds to the ideal exit enthalpy. So now our pH diagram is showing us the work transfer associated with the real turbine. That's the difference between HI and HE real. And it shows us the work transfer that's associated with the ideal process, the ideal turbine. That's HI minus HE ideal. And now we can see how the ideal turbine gives us maximum work. And that's shown here in this, this inequality, where the difference between HI and HE ideal, this is the ideal work transfer, is greater than HI minus HE real, this is the real work transfer, that means that the ideal work for a turbine is greater than the real work for a turbine. And of course, that all makes sense. I mean, what I just said there, if I actually think about it, it's funny. We know that already. But what we've shown is how first and second law tell us how to do that. Okay, and that's what's important in this whole discussion, is using the first and actually mostly the second law of thermodynamics to confirm for us what the ideal process is. Okay, so far, all of our analysis has centered on the turbine, and of course I like to study turbines because they start with the letter T, and I have a certain fondness for the letter T. But we can, in fact, conduct very similar analysis for a compressor or a pump. The mathematics or the equations are exactly the same. The only difference is that in the case of a compressor or a pump, because we're putting work into these systems, we want to minimize that work transfer. So in the case of the turbine, we're trying to get work out of the turbine, so we want to maximize that work. In the case of a compressor or a pump, we're putting work into the device, and so we want to, in fact, minimize that work transfer. Okay, so what that means, though, that's really the only difference. That still means that we want the exit state to be as low as possible. Okay, but of course, because we're putting work into the system, the exit state will be higher than the inlet state. So what the second law tells us is how close to the inlet state can the exit state be while still transferring work into the system. Okay, so we can again do our TS and pH diagrams, and they basically look as follows. So again, what I'm going to do is I'll walk you through this as if I were talking about it in class, which again, since this is already all drawn out for you, it's not intuitive to see that. But we have, first of all, our line of constant pressure that corresponds to our inlet pressure, and our line of constant temperature that corresponds to our inlet temperature. And where those two lines intersect is our inlet state, so state I. We then have our line of constant pressure that corresponds to the exit pressure, and just like in the case of a turbine, this exit pressure is a fixed boundary condition. This exit pressure is going to be the same regardless of the device that we're studying. So in the case of the real compressor or the real pump, there will be entropy generation. So the exit entropy for the real process will be greater than the inlet entropy because of that entropy generation. And so we can say that this intersection here, where we have the real exit entropy that intersects the exit pressure, is our real exit state, and that corresponds to a real exit temperature. If we look at the ideal compressor or the ideal pump, in that case there is no entropy generation, so the ideal exit entropy is the same as the inlet entropy, and so where those 2 points intersect, the ideal exit entropy intersecting the fixed boundary condition exit pressure gives us our ideal exit state. And that, of course, then controls or dictates to us what our ideal exit temperature is. So what the TS diagram tells us is that in the case of the ideal process, the ideal exit temperature will be less than the real exit temperature. So let's take that piece of information and go to our pH diagram. And so we have now our line of constant temperature that corresponds to, I'm starting down here. Our line of constant temperature that corresponds to the inlet state, and our line of constant temperature that corresponds to the ideal exit state. And based on our analysis on the TS diagram, we know that the real exit temperature is greater than the ideal exit temperature. And so we draw our line of constant temperature for the real exit state to be greater than the line of constant temperature for the ideal exit state. So we then have our line of constant pressure for the inlet state, and so where Pi intersects Ti, that gives us our inlet state, and that corresponds to an inlet enthalpy. We then have our exit pressure, our line of constant pressure for the exit state, and again that's going to be the same for both the ideal and real processes. So where that exit pressure corresponds or intersects with the ideal exit temperature gives us our ideal exit state. So this E comma ideal is our ideal exit state, and we drop this down to get our ideal exit enthalpy. Likewise, our real exit temperature is higher than the ideal exit temperature at the same exit pressure, so this gives us our real exit pressure, our real exit state, this E comma real, and then that tells us what our real exit enthalpy is. And so if we now take a look at these differences, we see that HI minus HE ideal, that's the work that we have to put in to bring the exit state up to its ideal exit state, and the difference between HI and HE real is the amount of work that we have to put into the real compressor or pump device to bring the exit state up to the real exit state, okay? And so since HI minus HE ideal, so this difference is smaller than this difference between HE real and HI, so since HI minus HE ideal is less than HI minus HE real, and since HI minus HE ideal is the ideal work, and HI minus HE real is the real work, we can see that the ideal work into a compressor or a pump is less than the real work into a compressor or a pump. Okay, so there's more that we're going to talk about in just a minute, but before we do that, I very quickly want to discuss with you what it means to have an ideal compressor or an ideal pump versus a real compressor or a real pump. Very often, people think that the ideal compressor or the ideal pump, because it's ideal, it has no losses in it, should mean that we can bring the exit state to a higher pressure than the real compressor or pump, okay? But in this analysis, remember that we fix that exit pressure. That exit pressure is a fixed boundary condition. So your thinking is correct, but where it manifests itself is in this work term, okay? In other words, if I'm your customer and I want you to design a compressor or a pump for me, I'm going to tell you, I need my exit pressure, I need your pump to deliver pressure at X PSI. So that's a fixed constraint for you as an engineer. So your job then is to design that pump to deliver that pressure with as little work as possible. And that's where now this idea of ideal versus real manifests itself. If you design a real shoddy, if suppose you got your degree from TU and you design a real lousy, or say the TU engineer designs a real lousy pump, it's going to take a lot of work to bring that substance up to the desired exit pressure. Whereas if an Aggie engineer comes along and designs that pump with a lot fewer internal losses, closer to the reversible situation, closer to the situation where there's zero entropy generation, then the work that's required to bring that exit pressure up to the desired state is less. Okay, so that's what we're doing, is we're minimizing that work rather than maximizing the exit pressure when doing ideal work analysis of a compressor or a pump. Okay, so moving on then, what this whole discussion hopefully has surfaced for you is we can relate the performance of a real device to what its performance would be if it were an ideal device. In other words, we can define the ideal device. We can define the ideal process, and we can evaluate using our engineering tools the real process, and we can compare the two. We can ask ourselves, how good is the real process compared to if this were an ideal process? Okay, so by virtue of that possibility, we introduce a special type of what we call an efficiency, and we call this an isentropic efficiency. So all semester long, we talk about several different types of efficiencies, and for the most part, the general definition of efficiency is what you get divided by what you pay for. The one exception to that definition is isentropic efficiency. Isentropic efficiency is not what you get divided by what you pay for. And in fact, in a lot of ways, if you're ever curious about what people who study and talk and think about thermodynamics all the time, if you're curious about what we talk about, this is one of the things that we talk about. Should we call this isentropic efficiency, or should we call it something else? Should it be called isentropic coefficient of performance, or isentropic effectiveness, or what's a better term for it than efficiency? And the reason why we have these debates is because it doesn't fit that classic definition of efficiency of what you get divided by what you pay for. Regardless, that's what it's called. That's what your textbook calls it. That's what people out in industry call it. That's what I call it. And so we just need to be very careful about the conceptual sidestep that we're taking here. Okay, so how do we, since isentropic efficiency is not defined as what you get divided by what you pay for, how do we define it? Well, the definition of isentropic efficiency depends on the device that's being analyzed. Okay, so to further complicate things, there isn't a single standard definition for isentropic efficiency. Okay, there are different definitions for turbines and compressors / pumps. Okay, so let's start first of all with defining the isentropic efficiency of a turbine. So the way we write this is we use the Greek letter eta, just like we do for any other efficiency. The standard, we use eta for the general definition of efficiency of what you get divided by what you pay for. But what we do is we subscript this eta with the letter S, where this letter S indicates that it's an isentropic efficiency. And because isentropic efficiency depends on the device that we're analyzing, we further subscript it with the letter T to indicate that this is the isentropic efficiency definition for a turbine. So in words, the isentropic efficiency definition for a turbine is what we actually get divided by what we ideally get. So mathematically, this is written as the real work, that's what we actually get, divided by the ideal work. That's what we ideally could get, okay? Now, because there's this small change in wording, it's kind of hard to write this as what we get in reality, so I write it as what we actually get. And that's also what your textbook uses, what we actually get. So what I do is I'll just kind of also say that this real work is also often called the actual work. And so this isentropic efficiency definition for a turbine is actual work divided by ideal work. And when we do real rigorous isentropic efficiency analysis, we'll drop this whole actual work definition and just call this W sub A. So this W sub A is the actual work. And because the ideal work is that which results from the isentropic process, which isentropic means constant entropy or constant S, we will sometimes write the ideal work as W sub S, where this S, just like it represents isentropic over here in the description of efficiency, this S represents the isentropic work or the ideal work. So the definition of the isentropic efficiency for a turbine is the actual work divided by the isentropic work. If we're talking about a compressor or a pump, it's just the opposite, right? So in the case of a compressor, we're putting work into the device, okay? So we need to actually invert our ratio. and we get that the isentropic efficiency for a compressor, so now we use the letter C for compressor, or we could do the same thing for pump, where we would use the letter P here for pump. So this is defined as what we ideally put in divided by what we actually put in, okay? So of course our numerator then is the ideal work transfer, and the denominator is the real device work transfer. And again, just like we did with the turbine, we'll sometimes call that real work actual work. So we can write this as the ideal work divided by the actual work. And then if we apply our subscripts, our ideal work is W sub S, the isentropic work, and the actual work is W sub A, the actual work. Okay, so now, how do we actually go about doing isentropic efficiency analysis? Okay, so there's a few things to note, and the first to note is that you're always, whenever you do isentropic efficiency analysis, so if you are asked to calculate the isentropic efficiency of a process, or if you are given the isentropic efficiency for a given process and you have to calculate other parameters, the following are the consistent three assumptions / truths that you will always make when doing isentropic efficiency analysis. Okay, so the first is that you will always assume that both the ideal and the real device are adiabatic. Both devices are adiabatic. Okay, so even though it's a real device, and in the most precise definition, the most theoretical way, a real device is never perfectly adiabatic. That is true. But usually the real device is insulated so heavily that it can be reasonably modeled as being adiabatic. So when we do isentropic efficiency analysis, both the ideal and the real device are treated as being adiabatic. The second truth, in fact, this is more than just an assumption, this is in fact a physical truth, the ideal and the real devices would have the same inlet state. Okay, so your state I is the same for both ideal and real devices. And then the third, which is also a truth, this is a physical truth because of that physical boundary condition that we talked about earlier, both the ideal and the real device have the same exit pressure. Okay, so always remember to apply these three assumptions / truths when you do your isentropic efficiency analysis. Okay, so let's see real quickly how much time I have. So, we've only been at it for 45 minutes. So I have some time, in fact, to go through an example with you. So let me proceed to do that. Let me get this back into the reading mode here. Okay, and let me minimize this fellow. Okay. Okay, so now let's take a look at the example that we have. So this is our example. We have air. So air is our working substance. And remember that air is an ideal gas. And it's expanded from 2 megapascals in 327 degrees Celsius to 100 kPa. So the inlet state is Pi equals 2 megapascals, Ti equals 327 degrees C, and PE, the exit pressure, is 100 kPa. And it's done so in an adiabatic turbine. Then we're asked to determine, or we're told, to determine the isentropic efficiency of this turbine if the air is exhausted at 0 degrees C. Okay, so let's just take a look at this problem statement. And, we've already deciphered the first pieces of information that were given to us. But this last piece of information is very interesting. And we know, based on the discussion that we just had, that our exit state depends on if it's the ideal exit state or the real exit state. So what do you think this might be? We're told to determine the isentropic efficiency of the turbine if the air is exhausted at 0 degrees C. Do you think that's the real exit temperature or the ideal exit temperature? Well, I guess I don't know what you said precisely, but I'm hoping that you said that it was the real exit temperature, right? And so if you said it's the ideal exit temperature, you might be scratching your head thinking, okay, how do I know? How am I supposed to know this? Remember that you're being told to determine the isentropic efficiency of the turbine. If this were an ideal turbine, such that this was the ideal exit state, the ideal isentropic efficiency, or the isentropic efficiency of the ideal turbine, is 100%, right? So you wouldn't have to do any analysis at all. It's already known to you that the ideal exit, or the isentropic efficiency of the ideal device is 100%. Okay, so by virtue of it telling us that, that we're expected to calculate an isentropic efficiency, this is likely the real exit temperature. Okay, and I said likely there because you never know. Maybe this is an ideal turbine, and we will go through our analysis and we'll find out that this, in fact, is the same as the ideal exit state temperature, in which case we would calculate our isentropic efficiency to be 100%. Okay, but this is exit state temperature for the turbine that we're analyzing, and so we have to treat that as the real device. So we treat this as the actual exit state temperature, or the real exit state temperature. Okay, so let's go ahead and set this analysis up. So I've rewritten the problem statement up here, and we have our turbine with an inlet state, and it's an actual turbine, so it's producing actual work, and we have our actual exit state, E comma A. And I write down our inlet state information. Ti is equal to 327 degrees Celsius, Pi is equal to 2 megapascals, and our exit state pressure, 100 kPa, and our actual exit state temperature, 0 degrees C. And so we say that, we of course make some statements about our process. It's a turbine, and even though it's not explicitly stated that we can assume it's steady state, we will impose the assumption that it's a steady state device, and it's an actual device, and so we're being tasked with finding the isentropic efficiency for this turbine device. Okay, so let me just remind you of some of the assumptions / truths that we make with isentropic efficiency analysis. We, of course, will say that both turbines, right, so the ideal and actual turbine, are adiabatic. So in both cases, Q is equal to 0. And the one truth is that the exit pressure for both turbines is the same, right, for both the ideal and the actual turbine. And the other truth is that the inlet state of both turbines, the ideal and actual, is the same. I have our same here, but I don't think that's proper English. I apologize. So the inlet state, that's singular, is the same for both turbines, both the ideal and the actual turbine. Okay, and that's also a prevailing truth that will always be true when doing isentropic efficiency analysis. Oops, sorry about that. Okay, so let's first of all start with our first law equation, okay, just to get ourselves started. And so, and now the one thing that I didn't mention in the lecture material before doing this example is that when doing isentropic efficiency analysis, you'll have to do analysis for both the actual process and the ideal process. So you're going to have to write the first law for both the actual turbine in this specific example and the ideal turbine. Okay, so our first law, of course, tells us that heat transfer, and again, this is already imposing the assumption of it being a steady state process. It's a work device, so there's the work transfer here, and there's negligible changes in kinetic and potential energy, and it's single flow in, single flow out. Okay, so all those assumptions have been applied to this first law equation. So we get Q plus our inlet enthalpy is equal to our actual work, W sub A, plus our actual exit enthalpy. It's very important when doing this analysis to keep track of your subscripts, okay? Those subscripts, the reason why is that these values will change depending on if it's the actual turbine or the ideal turbine. So since we're writing the first law for the actual turbine, I subscript work with A, and I subscript my exit enthalpy with A to indicate that this is for the actual process. So rewriting the first law, I get that the actual work is equal to the inlet enthalpy minus the actual exit enthalpy. Okay, now we're going to recognize that air is an ideal gas. And so since air is an ideal gas, we know that the change in enthalpy for an ideal gas is the constant pressure specific heat times the change in temperature, delta H equals Cp delta T. So we can say that the actual work is equal to Cp times Ti minus Te comma A. Okay, the inlet temperature minus the actual exit temperature. We know both Ti and actual exit temperature. We know both of these values. We can look up Cp in our tables, so we can actually calculate the actual work for this turbine right now. We can calculate W sub A. Okay, so if we look at our definition for the isentropic efficiency for the turbine, it's the actual work divided by the ideal work. We need to calculate this. That's what we're tasked to do. We know W actual, so we just have to figure out W ideal. Okay, so the question is how do we find the ideal work transfer, W sub S? Well, the way that we find that is we now change our control system analysis to the ideal turbine, right? So rather than focusing on the actual turbine, we'll now focus on the ideal turbine. So the first law for the ideal turbine is the following. We have the same first law, Q plus HI, is equal to now our W sub S, the ideal work transfer, plus the ideal exit enthalpy, HE comma S. So we rewrite this to solve directly for W sub S, since that's what we want. And W sub S is equal to HI minus HE comma S. And again, we know that air is an ideal gas, so this delta H is equal to Cp delta T. Okay, so if we look at this Cp delta T, I know Ti, but I don't have a value for Te comma S. I don't know what that ideal exit temperature is. So now my question is, what is the ideal exit temperature? What is Te comma S? Okay, well, we already know based on this whole discussion from the lecture material that exit temperature, the ideal exit state temperature, is the temperature of the exit state if the process were ideal. In other words, it's the temperature that corresponds to when the exit entropy equals the inlet entropy. It's the exit temperature that corresponds to the isentropic process. Okay, so Se comma S is equal to Si, or the change in entropy through the device is equal to 0 for the ideal process. Okay, well, I have an equation to relate the change in entropy of my ideal gas to other properties, right? Remember that the change in entropy for an ideal gas, delta S, is equal to Se comma S minus Si, right? That's the change in entropy of my ideal gas through the turbine. And delta S for an ideal gas is equal to what's on the right-hand side, the constant pressure specific heat times the natural log of the temperature ratio minus the gas constant times the natural log of the pressure ratio. That's a P there, P sub I. It looks a little bit like gamma. Sorry about that. So because I'm doing this for the isentropic process, that means that my exit state temperature will be Te comma S, right? It's the exit temperature that corresponds to the ideal exit state. And because it's an isentropic process, my change in entropy is equal to 0. So my left-hand side is equal to 0. So I get that 0 is equal to Cp times the natural log of my temperature ratio between the ideal exit state and the inlet state, minus R times the natural log of my exit pressure divided by my inlet pressure. Well, if I take a look at this, I have one unknown because Ti is known, Pe is known, and Pi is known. I can look up Cp and R in my tables. So I have one equation and one unknown. I can use this equation to solve explicitly for the ideal exit state temperature, Te comma S. So I algebraically manipulate this equation, so I solve directly for Te comma S. So I get Te comma S is equal to Ti times Pe over Pi raised to the R over Cp. So now all I need to do is look up R and Cp in my tables, okay? And so when I do that, I find that R is equal to 0.287 kilojoules per kilogram Kelvin. I get that from either table A1 or it's also in table A2A for air. And the CP value is 1.005 kilojoules per kilogram Kelvin, and I get that from table A2A. Okay. The only thing I need to be careful about is when I plug in temperature here, Ti, I have to be careful to convert that to Kelvin. Okay. Most of you did that successfully on the first exam, so I congratulate you for that. So, and if you're ever curious, it's always safe to convert temperature to absolute. You'll never be wrong by converting your temperature to absolute. Okay. So 327 degrees Celsius, that's my inlet temperature. That's 600.15 in Kelvin. And so now I can plug all this good stuff into my ideal exit state temperature equation and get that my ideal exit state temperature is 255 Kelvin. Now I have my inlet temperature, my ideal exit state temperature, my CP value. I can calculate my ideal work transfer, W sub S, and that comes out to 347 kilojoules per kilogram. And I already knew these parameters before, but I'll just now plug in the numbers. I can calculate the actual work, and the actual work is 329 kilojoules per kilogram. So now I have the two pieces of information I need to know to calculate the isentropic efficiency for a turbine. And so that is the actual work divided by the isentropic work. And when I plug that in, I get that the isentropic efficiency for the turbine is 94.8%. Okay, so in fact, that's actually very good. So isentropic efficiency, as we already talked about, could theoretically be 100%. You could have potentially a maximum efficiency equal to 100%. And usually what this isentropic efficiency tells you is it quantifies for you the loss in work transfer due to internal irreversibilities. And since for most of this equipment, your most significant irreversibilities are friction, what this really tells you is the amount of energy that, or the amount of work transfer that you're losing due to friction. Okay, and so these efficiencies tend to be very high. Greater than 90% is actually very commonly found in practice. And how engineers actually use this isentropic efficiency is by doing helping with diagnostics. So, for example, if you're operating a steam power plant, you're constantly measuring your inlet and exit temperatures and pressures. And since you're using steam, for example, in a steam power plant, you can determine your inlet and exit enthalpy and entropy and do an isentropic efficiency analysis on that process. And so, as time goes on, if that isentropic efficiency drops, that's an indication to the plant engineer that there's something starting to go wrong with that mechanical device. Either a bearing is starting to go bad, or something isn't being lubricated properly, but it's used as diagnostic information. Okay, so with that, in fact, I did not use the full 75 minutes, but I know I'm always running over in lecture anyway. So, and I also want to give you time to fill out your mid-semester course evaluation. So maybe use the next 15 minutes to do that, or use it to watch the enhancement lecture. So in fact, I have another example problem that walks you through isentropic efficiency calculation, as well as just doing general steady state work problems. So there's those two examples that you can watch as well. So with that, I'll close the lecture. If you have any questions, please send me an email. Thanks very much for your time and attention, and gig that thermodynamics. Bye.